Question 7. Hydrogen can be made by the reaction of methane with steam, and the equilibrium is given below. Use Le Chatelier's principle to predict the effect of the equilibrium yield on hydrogen if the overall pressure is increased. Well, hydrogen is on the right hand side. So pressure is related to volume. So let's have a look at the volume of the gases, the number of moles of gas on the left hand side. I've got 1 and 1 is 2 on the left hand side, and I've got 1 and 3, 4 on the right hand side. So I've increased pressure by Le Chatelier's principle. It'll try and oppose that change and lower the pressure. It can lower the pressure by decreasing the volume and shifting the position of equilibrium from the right hand side down to the left hand side. And therefore, if it shifts the position of equilibrium to the left, therefore it decreases the amount of hydrogen. Explain why the equilibrium yield of hydrogen is unchanged if a catalyst is used in the reaction. Well, a catalyst speeds up both the forward and the backward reaction, but by the same amount, so you don't get any effect on the position of equilibrium. (7.3) I've got some data for each of the standard enthalpies of formation. And also I've got entropy, but the first part of the question is about the standard enthalpy change, so I'm just going to use the first row of data. So I know my equation, CH4 plus H2O makes CO plus 3H2 from the first part of the question. My elements in their standard states are as you'd find them in the lab, so carbon as a solid, hydrogen as a gas, oxygen as a gas. And I've got the reactions here. Enthalpies of formation are enthalpy changes when you convert elements from their standard states, as you normally find them into the lab, into each of these substances. So I've got each of the values to make CH4 from carbon solid and hydrogen gas, as you normally find carbon and hydrogen in the lab, minus 75. To make water from hydrogen and oxygen, minus 242. To make carbon monoxide from carbon and oxygen, minus 111, and to make hydrogen from itself, unsurprisingly, nothing, because you're just converting hydrogen into hydrogen, you're not even doing the conversion. Now then, you're asked for the enthalpy change for the reaction to convert CH4 and water into CO and 3H2, so I've got to take these chemicals on the left, the CH4 and the H2O, and turn them into the ones on the right, and I'm going to use this alternate route here. So I'm going to reverse this sign from minus 75 to plus 75, reverse this one from minus 242 to plus 242, and these two are going in the right direction. We've got 1 mole of this, 1 mole of this, 1 mole of this, and 3 moles of hydrogen. So I'd multiply this 0 by 3, but 3 zeros are 0, so I can leave that alone. So my enthalpy change is plus 75, plus 242, minus 111, and 0, 206, and it's in kilojoules per mole, because the other enthalpies are in kilojoules per mole. Use your answer from 7.3 and the entropy to calculate the minimum temperature needed for the reaction to be feasible. Okay. So what have I got? I've got delta S, which is my enthalpy change, is the my entropy change, which is the entropy of the products take away the entropy of the reactants. So you've got to remember that equation. So entropy change is entropy of the products, the things you're making, take away entropy of the reactants. So entropy of the products is a 198 and a 131, but I'm making 3 moles of H2. So I've got 3 moles of H2 made, so I've got to multiply by my 131 by 3. And then I take away the entropy of the reactants, so that's 186 minus 186, because I'm taking it away, minus 189, because I'm taking it away, and my entropy change is 216. Now delta G equals delta H minus T delta S. My delta H I've got from the first part of the equation, 206 kilojoules, but I've got to get that into joules. That delta H has got to be in joules, so I'm converting a large unit like kilojoules down into a smaller unit like joules and multiply by 1,000, so that's 206,000. Now, delta G, when it's 0 or less than 0, then the reaction becomes feasible. So the first point it becomes feasible is when it's 0. So if I have delta G as 0, that's going to be the first point that it becomes feasible, and that will be my minimum temperature required. So I'm going to have delta G as 0, delta H is 206,000, which is my enthalpy change in joules. Take away my temperature, which I don't know, and 206 is my entropy change. So if I reverse both sides, if I take 206,000 across to the other side, it becomes minus 206,000 equals minus T times 216. Make both minus signs positive, so 216 times T is 206,000. Divide both sides by 216. T is 953.7 Kelvin. It asks for it, however, in degrees C. So to convert this Kelvin into into degrees C, I've got to take away 273, and therefore that's 680.7. In terms of significant figures, all of the values are to 3 significant figures. So I'm going to convert this to 3 significant figures. I'm going to turn 680.7 into 681 degrees C.